Testing. 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 Okay. Testing. We're live. Sound is working. Let's make sure all of our stuff is in order. Okay. Welcome to another Hoopo stream. Today we're going to be doing some hyperparameter tuning. So specifically we're going to be looking at the tuning playbook, which is a public GitHub repo out of Google Research, where they basically compiled a bunch of best practices and tips and tricks for hyperparameter tuning. So we're going to go ahead and read these. We're maybe going to explore some of the different tools they recommend and go through some of the tricks that I use when I do hyperparameter tuning. All right, so let's get started. What is this document for? This document is for engineers and researchers interested in maximizing the performance of their deep learning models. We assume basic knowledge of machine learning and deep learning concepts. The emphasis is on the process of hyperparameter tuning. We touch on other aspects of deep learning training, such as pipeline, implementation, and optimization, but mostly hyperparameter tuning. The machine learning problem is a supervised learning problem. So this is not necessarily the case a ton of the time anymore. I think unsupervised learning approaches are more and more popular, but generally if you're doing machine learning at home or in a small team inside an organization, you're going to be doing supervised learning. Generally unsupervised learning is the realm of large companies trying to build foundational models. Some of the prescriptions in this document may also apply to other types of problems. So, all right, let's see what they have to say. There's an astonishing amount of toil and guesswork involved in actually getting deep neural networks to work well in practice. Yeah, it's still very much kind of dealing with the black box nature of deep neural networks. You have to do what are called basically these hyperparameter sweeps, where you try out your training pipeline with a variety of different parameters, right? There's different magic numbers in your training pipeline, and it's very difficult to know which number is going to perform better than the other number, which setting is going to perform better than the other setting. So the only way to really do it is to kind of try them all and then see which one does best. The actual recipes people use to get good results are rarely documented. Papers gloss over the process that lead to their final results in order to present a cleaner story, and machine learning engineers working on commercial problems rarely have the time to take a step back and generalize their process. Textbooks tend to eschew practical guidance and prioritize fundamental principles, even if their authors have the necessary experience in applied work to provide useful advice. When preparing to create this document, we couldn't find any comprehensive attempt to actually explain how to get good results with deep learning. Instead, we found snippets of advice in blog posts, social media, tricks peeking out of the appendix of research papers, occasional case studies about one particular project or pipeline, and a lot of confusion. There's a vast gulf between the results achieved by deep learning experts and less skilled practitioners using superficially similar methods. At the same time, these experts readily admit that some of what they do might not be well justified. As deep learning matures and has a larger impact on the world, the community needs more resources covering useful recipes, including all the practical details that can be so critical for obtaining good results. So, yeah, to me the main points here are that any kind of deep learning course, any kind of paper that you read, they don't really talk about the hyperparameter tuning part of it, right? They cherry pick the best performing models, and really they just talk about what the best performing models are doing. But with almost any deep learning project, 90% of the models you're going to train are basically you're just going to throw away. And over the course of a project, you'll kind of iterate on some things and update some things, and then it's really only at the very end, the very final model that you produce, that is actually doing anything useful. And there's a lot of worthless, dead models on the way to that point. So who are the authors? Is a team of researchers and engineers working in speech recognition, astronomy. Although it has been gratifying to see deep learning go from a machine learning approach practiced by a handful of academic labs to a technology powering products used by billions of people, deep learning is still in its infancy as an engineering discipline, and we hope this document encourages others to help systematize the field's experimental protocols. This document came as we tried to crystallize our own approach to deep learning, and thus it represents the opinions of the author at the time of the writing. Yeah, this is just kind of the sacred text, but there's nothing fundamental here, right? Like, these are tips and tricks that apply to specific deep learning hyperparameter tuning, but the underlying mathematical reasoning of some of these things is not really understood. It's more the result of scientific experimentation, right? Our intention for this work is to be a living document that grows and evolves as our belief changes. Let's see how much that's actually happened. So you can go here, look at the README on GitHub, and we can look at the history. First commit for the tuning playbook 3 weeks ago. Answer FAQ about tuning batch size 3 weeks ago. So yeah, this is a relatively recent file here, just 3 weeks ago. All right, let's keep going. We're almost here. We do not know the optimal deep learning recipe, but until the community starts writing down and debating different procedures, we cannot hope to find it. To that end, we would encourage readers who find issues with our advice to produce alternative recommendations. Yeah, so they're encouraging peer review and kind of discussion, which I think is important, right? They're not trying to position themselves as kind of experts and truth sayers. They're basically saying, hey, these are just a bunch of tricks that we have, but if you found these tricks to not work in your specific problems, we'd love to know. Any sections marked with the robot emoji are places we would like to do more research. Okay, our guidance below makes the following assumptions. So this is guide for starting a new project. Enough of the essential work of problem formulation, data cleaning has already been done that spending time on model architecture and training configuration makes sense. This is a pretty big assumption, because I think for the majority of problems, when you first approach them with the intention of using a deep learning solution, data cleaning is a huge part of it, right? Exploring your data, doing what's called exploratory data analysis. So going through your data, understanding kind of the distribution of the different properties of your data, seeing if there's any mislabeled data, especially if you're doing supervised learning. Problem formulation, like what are going to be your inputs and your outputs to your network. There's a lot of stuff to be done here, and I would say that actually the time you spend working on problem formulation and data cleaning is a lot more important than the time you spend on model architecture and training configuration. So this is kind of a very important assumption here, because in academia, when you're doing research, generally the data you're using is a public data set or a benchmark, so you don't have to worry about that data being clean because someone already went ahead and cleaned it for you. But when you're working in an actual real-life industrial scenario, the data is not going to be clean, and you're going to spend the majority of your time actually cleaning this data set. Especially if you're at a startup or a smaller team and there isn't like a dedicated data engineer or anything like that, and you are and as a machine learning engineer, you're kind of in charge of not only just the model architecture and the training, but also the data part of that. There's already a pipeline set up that does training and evaluation, and it is easy to execute training and prediction jobs from various modes of interest. This is not as strong of an assumption. I think pipelines for training and evaluation are relatively easy to do now. Over the years, right, we've seen a ton of different machine learning frameworks, everything from Keras to PyTorch to TensorFlow to JAX to Gluon. There's so many different machine learning frameworks, and all of them have different examples for training and evaluation pipelines. And you probably should not be writing these yourself, right? You should just basically go find some examples of a training and evaluation pipeline for a specific framework that you want to use, and then just kind of copy paste that boilerplate and then just use it as a starting point. So machine learning engineering, a huge part of what you want to be doing is not double doing work. So machine learning is a lot of boilerplate. So the better you are at copy pasting boilerplate and letting other people do the work for you, figuratively, the faster you're going to make progress. The appropriate metrics have been selected and implemented. These should be as representative as possible of what should be measured in the deployed environment. I say metric selection is kind of, to me, part of problem formulation. Like, how am I going to measure the quality of my model predictions, accuracy, precision, recall? There's different metrics you can use, and depending on your problem, the metric is going to be very important, right? You can pick the wrong metric and then spend a bunch of time optimizing your models to improve a specific metric, and then it ends up not being super important for your use case. So when you're working on a problem and trying to figure out what the inputs and outputs are going to be and how you're going to measure performance, make sure you think about how important that metric actually is and whether it actually represents success in your use case. Because if you end up optimizing the wrong metric for a bunch of time, you're just going to waste a bunch of time. Choosing the model architecture. Okay, when starting a new project, try to reuse a model that already works. Yeah, you should really, very rarely should you be making a model architecture from scratch. Especially nowadays, there's so many example models and frameworks that provide a ton of different models for a ton of different problems that, unless you're working with very specific hardware that requires a different type of architecture, or you're working in a problem space with a type of data that is so weird that you need to use a custom architecture, you should really just try to use a well-established, commonly used model architecture. Model architectures typically have various hyperparameters that determine the model's size and other details, such as number of layers, the width of the layers, the type of activation function. Choosing the architecture really means choosing a family of different models, and then you're going to have some distribution of possible models within that. We will consider the problem of choosing the model hyperparameters in choosing the initial configuration and scientific approach to improving model performance. Actually, one second here, I'm going to put this link on the Discord. Just make sure people are there. Boom, boom. Go into our GitHub. We're going to copy paste a link to this stream. How do I do this? Share. Copy. Come here. We are live. Come check it out. Okay. Oh, nope, that's not what I want. Okay. All right, back to it. Choosing the optimizer. Starting with the most popular optimizer for the problem at hand, optimizer is going to be something like Atom. It's like kind of a type of gradient descent method, basically, is what you want to think of it as, right? It's like, at the end of the day, what you're doing with deep learning is you're basically calculating the slope and then using Newton's method or gradient descent to basically move in the direction of a slope. But there's a million different ways of doing that, right? So here you have stochastic gradient descent with momentum. You have atom and n-atom, which are also different types of gradient descent. So I would say you don't really want to be picking an optimizer separately from your model architecture. To me, if you when you pick a model architecture, there's going to be a training script or some kind of pipeline example for that, and there will be a optimizer that the authors of that script chose, right? And generally, you should probably just use that same optimizer. So, to me, the optimizer is almost a hyperparameter of the model architecture rather than something separate from the model architecture. No optimizer is best across all types of machine learning problems and model architectures. We recommend sticking with well-established popular optimizers, especially when starting a new project. Ideally, choose the most popular optimizer for the same type of problem. Yeah, I would even go as far as say choose the optimizer that is specifically used in the example that you're starting from. Be prepared to give attention to all hyperparameters of the chosen optimizer. Optimizers with more hyperparameters may require more tuning effort to find the best configuration. So optimizers such as Atom, there's these different parameters like these beta parameters in there. So that's kind of what they're referring to, that these optimizers that do gradient descent, right, they have these different momentum terms and these different little tricks and additional terms, but those additional terms generally have these weights in front of them that allow you to kind of like tune how important the momentum is, for example. And those weights are basically arbitrary, and you have to pick a number for them. There are defaults, so like here, for example, PyTorch Atom Optimizer. This one. Yeah, so if you look at the Atom Optimizer in PyTorch, you have your learning rate, and everybody's kind of used to the learning rate being a hyperparameter, but there's also these other things here, right? There's beta 1, beta 2, there's epsilon, and then there's weight decay. So here the default values are 0.9, 0.999, 1e to the negative 0.08, but really you could be tuning these. So it's important to realize that there's a lot of different hyperparameters you could be tuning. So the hyperparameter space can get really big really quickly if you actually want to sweep over the entire hyperparameter space. But most of the time you're better off just kind of either using the defaults, or in the example that you picked to start from, just use what they use. It may be preferable to start with a simple optimizer, SGD with fixed momentum, or Atom with a fixed epsilon, beta 1 and beta 2 in the initial, and then switch to a more generalized optimizer later. So these are the beta 1, beta 2, these are these numbers here, betas. Here they're as a tuple, right? A tuple where the 0th one would be beta 1 and then this one would be beta 2. Okay. SGD with momentum, Atom, and Atom. Are these like separate pages, or are these like links? Like what are these? Okay, they're like separate sections at the bottom. All right, we'll probably get to them though. All right, choosing the batch size. The batch size governs the training speed and shouldn't be used to directly tune the validation set. Often the batch size will be the largest batch size supported by the available hardware. Yeah, this is the truth right here. The batch size, you pretty much always want the biggest possible batch size, because every time you calculate gradients, right? When you're performing training, you're feeding a batch of data in through your model, and you're getting basically a batch of outputs for that batch of inputs. And then what you're doing with your gradient descent is you're basically saying, okay, I'm gonna, for each of these examples in the batch, there's some corresponding direction in weight space or parameter space that I want to move in, right? But for all of the stuff in the batch, I'm going to average basically all of those little individual movements in weight space that each instance of the batch gave me. So the bigger the batch you have, the more the less noise there is in that step, right? If you have a batch size of 1 and you're feeding an example 1 by 1, you might be taking gradient descent steps that aren't necessarily moving you in the right direction, right? There's kind of like a bunch of noise to that gradient step. And that's why some of these optimizers have things like momentum, right? Where basically it prevents a single step from moving away from the direction that this marble is rolling in a hill, to use the marble in the hill analogy of learning. So bigger batch size means more consistent, more smooth gradient steps. So generally the way that you end up doing this is that you think about what hardware am I going to be training this on, and then say, okay, if my model is whatever 1 gig and I have 2 gigs of memory on my GPU, then what's 1 gig worth of batch size? And you can do the math like that, or you can basically just run your batch size at 1, see if it works. Run your batch size at 2, see if it works. Make your batch size 16, see if it works. Make it 32, see if it works. Make it 64, see if it works. And just keep increasing the batch size until you get the out of memory errors, and then go a little bit lower than that. So that's maybe a little bit more practical advice there, where basically keep increasing the batch size until you get the out of memory errors, and then go a little bit lower than that. Increasing the batch size will often reduce the training time and also make it more smooth. This can be highly beneficial because it allows hyperparameters to be tuned more thoroughly and reduces the latency of the development cycle, right? The faster you can train, the faster you can iterate, the faster you can get to the final model, which is the one that's actually going to be doing all the stuff. Increasing the batch size may either decrease, increase, or not change the resource consumption. I don't know what that means. I guess you're just, if you're somehow super conscious about electricity usage, you could use a small batch size, but that seems terrible. I think if you're going to be using the electricity anyway, so might as well just try to use the biggest possible machine and with the biggest possible batch size. The batch size should not be treated as a tunable parameter for validation set performance. Yeah, you don't, like the validation data set, like the batch size doesn't actually matter for that at all, you know, because the validation set, it's more about, for example, like on validation, you don't do any shuffling, right? So in your training data set, every time you feed it through, every time you create a batch from your training data loader, you're shuffling that data because you want it to appear in a different order. You want each batch that goes into your model at training time to be shuffled, right? Different batch every time. But when you're doing a validation or a test set, you don't want any of that shuffling. You want it to be the same batches every time because you want to be able to measure performance and you want to see how good your model's doing over time. So when you're actually doing inference for the purpose of validation and testing, you don't want to be messing with the batch size and you don't want to be shuffling that. As long as all hyperparameters are well tuned, especially the learning rate and regularization parameters, so things like layer norm and batch norm, these types of regularization have a bunch of hyperparameters as well. So those, I would actually recommend those. You also want those to be as generic as possible. Try not to like mess with those hyperparameters, but I'm sure they have some advice for that part as well. And the number of training steps is sufficient. The same final performance should be attainable using any batch size. Okay. Why shouldn't the batch size be tuned directly to improve validation set performance? Because you're not doing anything. Okay, so they have a couple extra sections here. Determining a feasible batch size. For a given model and optimizer, there will be a range of batch sizes supported by the available hardware. The limiting factor is usually accelerator memory. Yeah, so it comes down to how much memory you have on your GPU is basically the point. And one way you can do this is if you go to your terminal, if you're using NVIDIA hardware, you can say NVIDIA SMI, and this part here of your NVIDIA SMI will tell you how much memory you have on your GPU. So I have a 3090 on this computer, so I have here 24 gigs of possible memory. So the model size plus the batch size has to be less than 24 gigs. Unfortunately, it can be difficult to calculate which batch sizes will fit in memory without running or at least compiling the full training program. Yeah, this is kind of why I was advocating the easiest solution is to run training jobs at different batch sizes, increasing by powers of 2 for a small number of steps until one of the jobs exceeds the available memory. Yeah, this is kind of what I was describing. It's the best way to do it. Just run it, make the batch size bigger, run it, make the batch size bigger, run it, make the batch size bigger, and then eventually you'll get a CUDA out of memory or some kind of like could not allocate tensor, some error that basically says that we ran out of memory on the GPU, and then at that point just go a little bit lower in the batch size, and that should be the batch size you use for training. And you're going to have to do that for every different type of machine that you use. So if you now switch and you're training on a different machine with a different GPU, you're going to want to redo that to figure out what the batch size is for that machine. For each batch size, we should train long enough to get a reliable estimate of the training throughput. Training throughput is the number of examples processed per second, or the time per step. Okay. I don't know if you necessarily need to calculate this. I think unless you're like doing, trying to figure out a way to optimize this and use better hardware, or advocate for different hardware, or convince someone that we should use more money, like knowing the exact number of steps per second isn't gonna help you get a better machine learning model. When the accelerators aren't yet saturated, if the batch size doubles, the training throughput should also double. If this is not the case, then the training pipeline has a bottleneck such as I/O or synchronization between compute nodes. So what they mean here is that there's two different ways that your training can be bound, right? Or can be bottlenecked. One way that it's bottlenecked is that the GPU itself, basically whenever it's doing these matrix multiplies, your batches and your models are so big that those matrix multiplies take such a long time that you're basically limited by the speed of the GPU itself. That was more so the case back in the day, but nowadays, really, usually what you're bottlenecked by is I/O, which means that loading your batch onto the GPU memory, right, or receiving the batch from some external compute node, right, is going to take longer than actually performing the matrix multiplies. And this is something we touched on in, I think we had an earlier video where we were looking at NVIDIA versus OpenAI Triton, and basically these different software modules that basically are in between your machine learning framework and then the actual hardware. And yeah, long story short, like most of the time now, training pipelines are limited by the speed at which data is shuffling between memory, right? So shuffling between your computer memory into the GPU memory, and then even within the GPU memory, there's different there's like caches that are closer to the actual cores that are performing the matrix multiplies. So I think generally as a kind of machine learning practitioner, you shouldn't have to worry too much about this. I think that just make sure you don't have something crazy where it's like waiting for a long time to receive data. But in terms of like actually optimizing the shuffling of memory around, unless you're really trying to squeeze the most performance out of your hardware, it's probably not worth spending a ton of time on. If the training throughput increases only up to some maximum batch size, then we should only consider batch sizes up to that maximum batch size, even if a larger batch size is supported by the hardware. I don't know. I would say there's advantages to using a larger batch size anyways, right? Because I think a larger batch size provides a more smooth learning signal, and like, so I feel like there's still an advantage to using the largest possible batch size than you can. Yeah, and different models are going to have a different, so this is important to realize. If you change your model, the amount of memory available on the GPU for your batch is going to change. So some models are going to allow for a bigger batch size than other models. Training time equals time per step times total number of steps. We can often consider the time per step to be approximately constant for all feasible batch sizes. This is true when there is no overhead from parallel computations and all training bottlenecks have been diagnosed and corrected. In practice, there's at least some overhead from increasing the batch size. As the batch size increases, the total number of steps needed to reach a fixed performance goal typically decreases. Yeah, so I mean, the faster you can chew through your data, the faster you're going to get to your final performance. The batch size that minimizes training time is usually the largest batch size. The batch size will depend on the data set, the model, and the optimizer, right? So if you're doing computer vision and you're using images, the batch size is going to be a lot smaller than if you're using a tabular data set, right? Images are very big, so they consume a lot of memory. So batch sizes for computer vision deep learning are generally way smaller than batch sizes for NLP, for example. So depending on what your data is, it's going to consume a different amount of memory, and your batch size is going to reflect that. Same thing, tiny model, you can have a huge batch size. If you have a really big model, you're probably not going to be able to fit a big batch size with it. And whenever you see in papers where they have these huge models with huge batch sizes, it's because they're using basically a parallel compute setup. So they have multiple machines with multiple GPUs, each calculating basically a potentially different there's different types of parallelism, but they're basically doing only a slice of the batch, maybe only a slice of the model, and that's how they can do big models with big batch sizes. But if you're training this on your kind of consumer GPU at home, or perhaps on like a Jupyter notebook in the cloud or something like that, you're generally the smaller models, you're gonna have a bigger batch size, and the bigger models, you're gonna have a smaller batch size. When comparing batch sizes, beware the distinction between an example budget epoch budget and a step budget. Comparing batch sizes with an epoch budget only probes the perfect scaling, even when larger batch sizes might provide meaningful speed up. Often, the largest batch size supported by the available hardware will be smaller than the critical batch size. There's no point in using a larger batch size if it ends up increasing the training time. I don't know. I think that don't decrease learning rate, increase batch size. Yeah, this is a famous paper that I remember. But here we show that one can usually obtain the same learning rate curve on both training and test sets by instead increasing batch size. Yeah, so this paper, I think, to me, showed that the greater batch size is not just about chewing through your data faster, but it's also because of the way that these optimizers work with momentum and so on. Like, they also give you just like a smoother signal to work with, right? Like, so I think in this here, they're kind of like simplifying it a bit too much and just basically saying that the only thing that batch size is, it's basically just a measure of how fast you're chewing through your training data set. But I think that there's also something to the kind of the fact that with big batches, especially with something that has momentum, right? Like these optimizers that have momentum, you are going to, it's learning differently. It's not the exact same type of steps that it's taking. It's taking slightly different steps that will end up in the local minima or global minima that you want. Choosing the batch size to minimize resource consumption. There are two types of resource costs associated with the batch size. Upfront, purchasing a new hardware, or rewriting the training pipeline to implement multi-GPU and multi-TPU training. Okay, and then usage costs, billing against the team's resource budgets, billing from a cloud provider, electricity and maintenance costs. Okay, so I guess if you already have a pipeline and now you want to say, okay, I want to make the batch size bigger, you're going to have to basically either figure out how to do data parallelism and like training in a parallel setup, and this can get quite complicated, so this is not insignificant, switching from a single GPU training pipeline to a multi-GPU training pipeline. And then, of course, the bigger batch size, the bigger hardware, the more it's going to cost, right? When you get machines from a cloud provider, the machines with the big GPUs are going to cost way more than the machines with the small GPUs. So there's also kind of a trade-off there in terms of like how important is it for you to train something quickly and train something with a big batch size for your business use case. Sometimes the business use case is not important enough to waste thousands of dollars on training. If there are significant upfront costs to increase the batch size, it might be better to defer increasing the batch size until the project has matured and it is easier to access the cost-benefit trade-off. Okay, implementing multi-host parallel training programs can introduce bugs and subtle issues. Yeah, this is like very complicated. Almost always not worth it, right? I think that you can get really, really far with just one GPU per machine running relatively simple code. I think that you should really only be considering parallel training once the machine learning project you've worked on has reached a level of maturity where there's probably multiple people now, you have containers, you're running things in the cloud. I think it's generally not worth the hassle to do multi-host parallel training unless you are already kind of pretty far along in your machine learning project. We refer to the total usage costs as the resource consumption. Increasing the batch size usually allows us to reduce the total number of steps. Whether the resource consumption increases or decreases will depend on how the consumption per step changes. Increasing the batch size might decrease the resource consumption. Increasing the batch size might not change the resource consumption. Increasing the batch size might increase the resource consumption. Yeah, so there's a lot of different ways that the batch size is going to impact how much you're billing, but changing the batch size requires retuning most hyperparameters. This is more interesting. The optimal values of most hyperparameters are sensitive to the batch size. Therefore, changing the batch size typically requires starting the tuning process all over again. The hyperparameters that interact most strongly with the batch size and therefore are the most important to tune separately from the batch size are the optimizer hyperparameters, such as learning rate and momentum, and the regularization hyperparameters. So, in our Atom optimizer, right, you have these hyperparameters here, and different optimizers are going to have different hyperparameters and different forms of regularization, such as layer norm, batch norm, are also going to have their own hyperparameters. Those hyperparameters are going to be specifically picked for a batch size, right? Because at the end of the day, what these numbers here are determining is basically the size and scale and direction of your gradient step, right? And your gradient step is going to be different if it's the gradient step is the result of a batch size of 2 versus a batch size of like 100, right? They're kind of like different magnitudes there. So there is kind of truth here where it's like you should be careful about messing too much with the batch sizes, because these kind of optimizer hyperparameters, especially if you're starting from an example project, are going to be picked for a specific batch size. How batch norm interacts with the batch size. So batch norm is a form of regularization where you normalize all the data within a specific batch. Batch norm is complicated and in general should use a different batch size than the gradient computation to compute statistics. See the batch norm section. Okay, so they have a whole little section for batch norm. Before beginning hyperparameter tuning, we must determine the starting point. This includes specifying the model configuration, the optimizer hyperparameters, and the number of training steps. Okay. Determining this initial configuration will require some manually configured training runs and trial and error. Our guiding pipeline is to find a simple, relatively fast, relatively low resource consumption configuration that obtains a reasonable result. Simple means avoiding bells and whistles. These can always be added later. For example, start with a constant learning rate before adding fancy decay schedules. So this isn't necessarily limited to machine learning. I feel like this is applicable to all forms of kind of programming and coding and computation, where it's like start from the simplest possible thing, create the simplest possible circuit, and then add complexity over time, because it's very difficult to have a very complicated system and debug a very complicated system. It's a lot easier to debug a very simple system. So first thing you do is take the simplest possible system, debug that, make sure it works, and then add complexity kind of piece by piece. And every time you add complexity, debug it again. So the only way to get to like a big complicated system that you're confident is bug-free is to basically build it layer by layer from the most simplest possible system. So if you're starting from an example project, don't start messing with a bunch of stuff in that example project right off the bat. Just try to see if you can run it as is, and then change things one at a time. Consumes minimal resources. Yeah, so this is kind of just like a tips and tricks here, but like when you're debugging, you're going to want to be able to run your whole training pipeline lots of times. So one thing that you can do is at the very beginning, just make a batch size of 1 or 2, train for like 2 epochs, right? Like use a small model. So just use like very small numbers for your hyperparameters, specifically batch size and the total number of training steps and the model size, so that you can basically run your training loop ideally in like basically like 30 seconds, so that you can test your training pipeline kind of end to end. Training for more steps can improve performance and makes hyperparameter tuning easier. Training for fewer steps means that each training run is faster and uses fewer resources. If you have early stopping, the number of training steps is also easier to tune. So early stopping is there's a lot of different hyperparameter tuning software, but most of them, I would say, have what's called early stopping, which is where the hyperparameter tuner can decide to stop training if it feels like the validation loss hasn't been getting lower or some specific metric hasn't been getting higher. And that prevents you from making the mistake where you train on something too long. Scientific approach to improving model performance. For the purposes of this document, the ultimate goal of machine learning development is to maximize the utility of the deployed model, even though many aspects of the development process differ between applications. Length of time, available computing resources, type of model. We can typically use the same basic steps and principles on any problem. All right. There is already a fully running training pipeline along with a configuration that obtains a reasonable result. I think if you start from an example project, that's usually the case, but getting to this point, if you're starting from scratch, is a huge task and 90% of the problem. There are enough computational resources available to conduct meaningful tuning experiments and run at least several training jobs in parallel. Yeah, I would say the important thing to realize here is that if you're on a laptop that doesn't have a GPU, you might never get to models that obtain reasonable results, and it's not because you're not coding well enough or your data set's not big enough. It's just because you're just not training long enough. There's a lot of people who just they don't have a GPU and they think that they can train, but realistically it's like you're not going to get very good results if your compute is just not strong enough. You should really, if you're going to be doing training at home, you should really try to kind of have a good GPU and be trained for a long enough time. If not, you should look into cloud providers where you can run many machines in parallel. Incremental tuning strategy. Start with a simple configuration and incrementally make improvements while building up insight into the problem. Make sure that any improvement is based on strong evidence to avoid adding unnecessarily complexity. Yeah, so this is kind of a little bit of what I was saying before, where just start with the simplest possible thing, debug that, and then incrementally add complexity. Don't add multiple things at the same time, right? A common mistake is you have your model and it works, your training pipeline works, and then you add learning rate scheduling and then batch norm and change the loss, and then you run it and it doesn't work anymore. And now you don't, because you added 3 different things, you don't know if what introduced the bug was the learning rate scheduling, you don't know if what introduced the bug was the batch or changing the layer normalization, you don't know if what it was the changing the loss function. So really try to incrementally add complexity over time and debug each intermediate step. Our goal will be to maximize how much we can improve a model by a fixed deadline. In other cases, we want to keep improving the model infinitely. We could maximize performance by using an algorithm to automatically search the entire space of possible configurations, but this is not a practical option. The space of possible configurations is extremely large, and there are not yet any algorithms sophisticated enough to efficiently search this space. I think the hyperparameter tuning frameworks would disagree, and they would say that they do have good algorithms. There's a lot of different HyperOpt. This is a hyperparameter tuning framework that I use myself, and here are some of the algorithms, right? You have random search, which basically just randomly searches within your hyperparameter space. You have TPE, basically different forms of statistical modeling within the hyperparameter space. So there's also kind of evolutionary based hyperparameter searching algorithms, and yeah, I would say that the algorithms are there, but I do kind of see what they're saying here, where for most problems the space of all possible hyperparameter settings is so huge that even if you had a very nice algorithm to search through it, it would still just take way too long to do that. So really, most of the time you're constraining that search space as a human. So there's some space of all possible hyperparameters, and then you as the human are picking some subset of that space, and you're saying, okay, I think these are kind of goodish values for these, and then within that limited subset or that limited space of hyperparameter space, that's where you set loose one of these hyperparameter tuning algorithms. Most automated rely on a hand-designed search space. Yeah, so this is the hand-designed search space is the human guidance. Most effective way to maximize performance is to start with a simple configuration and incrementally add features to make improvements while building up insight. Yeah, that's kind of the theme that we keep talking about here. our model will continually improve. Hopefully so, but not guaranteed. At high level, our incremental tuning strategy involves repeating the following 4 steps. Identify an appropriately scoped goal for the next round of experiments. Design and run a set of experiments that makes progress towards this goal. Learn what we can from the results. Consider whether to launch the new best configuration. Yeah, so this is basically, as a machine learning engineer, like once you get to the steady state, so initially you're going to be doing a lot of data cleaning, trying to understand the problem. Then you're going to be trying to find a good starting point, some example with some model framework that is similar to the problem you're trying to solve. Then you're going to be trying to basically reproduce the example, right? Make sure your code runs clean. Figure out what your hardware you're going to be running it on and tune the batch size and model size to make sure that it's specifically good for that hardware. And then you're going to probably end up with a model that does reasonably well, trains a little bit, you get some score, you can see the result, and you can go and present that to your boss and they can get business value out of it. And then what you're going to do kind of from then on is basically maybe once a week you come up with an idea of, hey, we want to add this additional functionality to our training pipeline. You add that functionality, you perform a hyperparameter sweep, you show that with that extra functionality you're getting better results, or you show that you're not getting better results. You present that to the team, and then you go back and do that all over again. So basically the steady state is you're running these experiments, usually at like a weekly cadence. And weekly cadence not because it takes you a week to implement, but because you need to run it long enough to matter, right? So especially if you have big data sets and big models, running a hyperparameter sweep can take a while, right? It can take a week for the models to just train, right? If you add something new and then you're training your models, but you're only training them for like 30 minutes, it's going to be very difficult to know if your models are getting anywhere because they're just you're not even giving them enough time to train. So don't be afraid to let your models run a little bit longer than you would think. I think a lot of times that's actually helped me, where it's just like nothing is working, and then you just let your models run for twice the amount of epochs, and then it just starts working. So definitely don't be afraid to let the models run. What do you think about auto hyperparameters? What is depends on what you mean by auto. The search space is defined by humans. So the auto yeah, Omar, like auto hyperparameters, like that can mean a lot of different things, but usually the hyperparameter space is defined by humans, and then the machine will pick values within that space. So, for example, here, yeah, like here, if you have something like this, right? So as a human, you're saying there's some variable called C2, some hyperparameter called C2, and it has values between -10 and 10. I want you, the computer, the hyperparameter tuner, to try a bunch of different values for C2 that are a uniform distribution between -10 and 10. So you as a human are telling the computer that the value it should find is somewhere between -10 and 10, but then the computer is finding the value for you that maximizes your objective, right? So automatic hyperparameters, just at the end of the day, you're still telling it -10 to 10, but the algorithm is the one that goes ahead and tells you, okay, well, within this range, here's the one that performs the best. exploration versus exploitation. Most of the time, our primary goal is to gain insight into the problem. I would say that it's very academic of them to suggest that. I think a lot of times when you're working at a startup or in a real world problem, your primary goal is to make money and to get the performance as high as you possibly can. Although one might think we'd spend most of our time trying to maximize performance, we spend the majority of our time trying to gain insight into the problem. In the long run, understanding the problem is critical if we want to maximize our final performance. Prioritizing insight over short-term gains can help us avoid launching unnecessary changes that happen to be present in well-performing runs merely through historical accident. Identify which hyperparameters the validation error is more sensitive to, which hyperparameters interact and therefore need to be tuned together. Yeah, this is an interesting reality too, is that a lot of these hyperparameters kind of they're not IID, right? They're not independently distributed. They kind of have some interplay. So when you're sweeping over these hyperparameter spaces, a lot of these hyperparameter tuners, for example, something like random search has no notion of any relationship between the hyperparameters. These more statistical ones, such as TPE and other kind of Bayesian optimization algorithms, they do try to model relationships between the hyperparameters, but they're very primitive, right? They're just based on like these Gaussian processes, and like, especially if your training pipeline is very long and you don't have a ton of examples, the Bayesian models that they are fitting to the interactions and the interplay between the different hyperparameters are going to be very primitive. So sometimes you need to understand the problem, I guess, as they're saying here, in order to make sure that the hyperparameter space that you're searching over is like valid and makes sense. Yes. Yeah, so the process isn't automated, is a bit too strong. So hyperparameter tuning libraries such as HyperOpt, another one is the Keras HyperTuner, this one, Keras Tuner, another one is 1B Sweep. So there's a bunch of different hyperparameter optimization libraries. Tune, another one is Ray Tune. So Ray has its own hyperparameter tuning library. So these are all different libraries that allow you to tune hyperparameters, but you know, at the end of they're not like magical, right? It's not like they're magically going to pick hyperparameters for you. You still have to define a search space, right? You have to define a specific search space for all of your hyperparameters, and all you're doing is just automating the process of running your pipeline with different hyperparameter configurations and then getting a final score from it. But choosing that hyperparameter search space is still very difficult, and that's basically what they're advocating for here. It's not this, all of this advice still applies even if you're using a hyperparameter tuning library. Recognize when improvements have saturated, narrow our search spaces around the optimal value. When we are eventually greedy, ready to be greedy, we can focus purely on the validation error. Choosing the goal for the next round of experiments. Each round of experiments should have a clear goal and be sufficiently narrow in scope that the experiments can actually make progress towards the goal. Each round of experiments should have a clear goal and be sufficiently narrow in scope that the experiments can make progress towards the goal. Example goals: try a potential improvement to the pipeline, understand the impact, and then maximize error. Yeah, so choosing the goal, I think it's a lot of times it's a team-based thing, unless you're kind of a N of one team and you're the only machine learning engineer on a specific problem. Generally, I think choosing what the next round of experiments should do, you should try to let other people in the team also give you advice in that, right? Let people kind of decide together what the next set of experiments should do, especially because a lot of times these experiments can get quite expensive, you know? Every time you train a whole bunch of models, it's going to cost a bunch of money. So letting people feel like they're part of that process, I think, is important. Just a little kind of hack. What's your favorite hyperparameter tuning framework, Omar? Identify which hyperparameters are scientific, nuisance, and fixed hyperparameters. Okay, so they're kind of classifying different hyperparameters into 3 buckets here. They're calling some scientific, nuisance, and then fixed. So scientific hyperparameters are those whose effect on the model's performing we're trying to measure. Nuisance hyperparameters are those that need to be optimized over in order to fairly compare different values. And then fixed hyperparameters will have the values fixed in the current round. These are hyperparameter values whose values do not need to change when comparing different values. Okay, I mean, this seems like kind of overly verbose and like taxonomical. Like, I don't think you necessarily need to like classify your hyperparameters into one of these 3 buckets. But in this framework, for example, fixed hyperparameters might be something like batch size, where you want to have all of your experiments use the same batch size. Nuisance hyperparameters might be, I don't know, things like data augmentation. So you're trying different types of data augmentation, and sometimes they work better, sometimes other ones work worse. So you just want to kind of sweep over a variety of them so that you have kind of a nice little statistical sample. And then scientific hyperparameters might be the ones that you're actually trying to figure out if they help or they don't help, right? So using a specific type of loss versus a different type of loss, right? You're trying to figure out, okay, did we change the loss and now we have loss B versus loss A? Is loss A better than loss B, or is loss B better than loss A? And that's the one that you actually want to kind of answer. That's the question you want to answer with this experiment. For example, if our goal is to determine whether a model with more hidden layers will reduce validation error, the number of hidden layers is a scientific hyperparameter. In that case, the learning rate is a nuisance hyperparameter because we can only fairly compare models with different number of hidden layers if the learning rate is tuned separately. The activation could be a fixed hyperparameter. Yeah, whether a particular hyperparameter is a scientific, nuisance, or fixed is not inherent and changes depending on the experiment goal. When designing a new round of experiment, identify the scientific hyperparameters. Yeah, it's like I feel like they're just kind of being needlessly, like, they're applying a bunch of labels to shit that doesn't need labels, right? You're at the end of the day, you have a bunch of hyperparameters, and you just kind of pick ones that you want to try, that you think might be doing things, sweep over the ones that you don't really know what they're doing, and then try to fix the ones that you don't care about at all, right? Or are set by something like the hardware. Like the batch size is determined by the hardware, so you shouldn't be sweeping over the batch size. Although the type we assign to each hyperparameter depends on the experimental goal, we have the following rules of thumb. Of the various optimizer hyperparameters, learning rate, momentum, learning rate schedule parameters, the betas, some of them will be nuisance parameters because they tend to interact with most other changes. They are rarely scientific because a goal like what is the best learning rate doesn't give much insight. Although we might fix some of them occasionally due to resource constraints or when we have particularly strong evidence that they don't interact with scientific parameters, we should generally assume that optimizer hyperparameters must be tuned separately to make fair comparisons. In contrast, the choice of optimizer is typically scientific or fixed. So are you picking atom or are you picking just SGD with momentum? I still generally feel like messing with the optimizer is not worth it. Just use the optimizer that is recommended and implemented in the pipeline that you start from. Generally, unless you're doing some kind of research type machine learning, don't fuck with the optimizer. That's just kind of a little tip. Hyperparameters introduced by regularization technique are typically nuisance hyperparameters, but whether or not we include regularization technique at all is a scientific or fixed hyperparameter. So whether or not we include the regularization technique, so for example, whether or not they have dropout, so no dropout versus dropout, no batch norm versus batch norm, no layer norm versus layer norm. So these different regularization techniques, yeah, you can add them or remove them. In some cases, the set of nuisance and fixed will depend on the values of the scientific parameters. Yeah, this is one of the most complicated things with hyperparameter tuning, is that sometimes your hyperparameter space is dependent on the hyperparameters. So if you have a hyperparameter that is some kind of categorical hyperparameter and has, for example, optimizer, and you can have either Nesterov or atom, these two choices for the optimizer actually have different hyperparameters themselves, right? The Nesterov momentum optimizer has a learning rate and a momentum hyperparameters, but then the atom optimizer has 4 hyperparameters: learning rate, beta 1, beta 2, beta, and epsilon. So when you're using these hyperparameter tuning frameworks, most of them are not very good at this. They can't change the hyperparameter space as they search over it, especially if they're using a something like a Bayesian modeling algorithm such as TPE, because in these type of Bayesian modeling algorithms, you can't change the space, right? The Bayesian algorithm is like, over time it's building some idea, or it's building this little Gaussian process model of like how the different parameters interact with each other. But if you change the space of those hyperparameters, now the model just breaks. There's nothing there. So I would say the hot tip here is just, in general, avoid any kind of hyperparameter space that changes depending on the different hyperparameters. If you have different hyperparameter spaces, just perform different sweeps. or different hyperparameter tuning runs. Don't try to have one giant hyperparameter sweep where the hyperparameter space itself is changing constantly. Creating a set of studies. How long is this? Should we be speeding up a little bit? Damn, look at all this. This is significant. All right. Let's try to speed up here a little bit. Okay, extracting insight from experimental results. In addition to trying to achieve the original scientific goal of each group of experiments, go through a checklist of additional questions, and if issues that are discovered, revise the experiments and rerun them. Each group of experiments has a specific goal, and we want to evaluate the evidence of experiments provided towards that goal. Yeah, so basically advocating for the scientific method here, right? Before you perform an experiment, have a hypothesis so that when you complete the experiment, you can then go back and say, okay, we had this hypothesis. These are the results of our experiment. What can we say about our hypothesis? And it's totally fine if it's wrong, right? It's totally fine if you said, okay, we're going to add dropout and we're going to see if it improves our performance, and then it doesn't, right? That's totally fine because you learned something, right? You went and you said, okay, well, at least now I know that dropout doesn't improve our performance. So with every experiment, every hyperparameter tuning sweep that you run, try to set a hypothesis, try to postulate a hypothesis beforehand so that you can basically then at the end of the experiment confirm or refute that hypothesis, and then as these authors here are saying, you can gain deeper insight about the problem. So kind of make sure that you're applying the scientific method and not just kind of trying a bunch of random things and not really moving anywhere. Is the search space large enough? Yeah, this is like extremely tricky, but like one thing you can do is if you're really not getting any results with your search space, you can make it a little bit wider. So for example here, this is the Keras hyperparameter tuning, but there's a choice here, right? This hyperparameter space has a hyperparameter called units, and the hyperparameter units has 3 possible choices. So your hyperparameter space has is basically just 3 points, 8, 16, and 32. So maybe you go and you basically run this hyperparameter sweep, and it turns out that all your results suck, and it doesn't seem like 8, 16, or 32 are leading to the result that you want. One thing you can do is expand your hyperparameter search space. So make this 2, 8, 16, 32, or 2, 8, 16, 32, 64, right? You're adding more possible choices for this hyperparameter units. So you're expanding the hyperparameter search space, and then maybe one of those points in the expanded hyperparameter search space will give you better performance than you're getting. So that's definitely something to think about. Is like sometimes think about the question, is the search space that I'm searching in big enough? Can I increase the range of some of these hyperparameters and increase the search space of some of these hyperparameters in order to potentially find better performance there? Have we sampled enough points? Yeah, if your hyperparameter search space is too big, you're not going to sample enough points in that search space. So there's a nice graphic, hyperparameter search space. This one. Let me see, this is the one I want. So let's say you had 2 hyperparameters, right? The search space for a 2 hyperparameter problem would be 2-dimensional, right? There's basically a bunch of, this is like just like it's hard to like explain this. I feel like I can explain it, but I don't, like, if you don't have my context in my brain, it's difficult to understand what I'm saying. But basically every time you run your hyperparameter tuner, what your hyperparameter tuner is doing is it's just picking a point in this hyperparameter space and then evaluating your training pipeline at that space, right? So for example, if you have a random tuner, so here, for example, in our hyperopt, random search. Random search is just going to basically randomly pick points in your hyperparameter space and evaluate them. And then it'll pick another random one and evaluate them. And over time, you'll get hopefully a good sample rate, a good distribution over your hyperparameter space. But other types of hyperparameter tuners, such as, for example, the TPE and these different types of Bayesian tuning algorithms, they'll actually kind of maybe get stuck in an area, right? Like they'll find one area of hyperparameter space where they got a good score, and then they just keep sampling from that area over and over and over again. So you have to be careful, because sometimes your hyperparameter tuners will kind of get fixated on a specific area of the hyperparameters, and then they won't explore outside of that. So make sure you look at what your hyperparameter tuning is doing and say, okay, am I searching sufficiently broadly over the area that I defined, or are all the points that I'm sampling either not enough points or just too concentrated? What fraction of the trials in each study are infeasible? Okay, so sometimes there's specific combinations of hyperparameters that don't work. That's fine. I think you just put a try catch in there, and if it errors out, just give it a really bad score, and then it won't try it again. So the model exhibit optimization issues. Based on the answers, refine the most recent study to improve the search space. Yeah, so you should always be constantly trying to refine your search space, right? Just over time, come up with a better and better search space. As you learn more and more about the problem, you're going to get better and better at picking a search space. So here, for example, the search space, this is a ray tune. There's a grid search. For the hyperparameter A, you have 4 different possible values here. You have 0.001, 0.1, 0.1, and 1.0. For the hyperparameter B, you have 3 possible values here. You have 1, 2, or 3. So your hyperparameter search space is actually 4 by 3. It's 12 possible values. So you should always be modifying and messing with this search space in your experiments. That's really, as a human, that's your job. Your job is to basically figure out the best search space, and then it's the hyperparameter tuning algorithm's job to figure out the best combination and permutation of hyperparameters within your search space. Identifying bad search space, not sampling enough points, examining the training curves. Damn, this is like a really expansive document. Like, what are we at? We're already at an hour 18. Okay, we gotta be a little bit faster. I'm gonna like skip over some of these sections here. Determining whether to adopt a training pipeline change or hyperparameter configuration. When deciding whether to make a change to our model or training procedure or adopt a new hyperparameter configuration, we need to be aware of the different sources of variation in our results. We might observe that a particular candidate change initially achieves a better validation error, but find that after repeating the experiment, there's no consistent advantage. Okay, so basically they say one thing you want to do here is try to figure out the training procedure variance, the retrain variance, or the trial variance. What is the variation we see between training runs but different random seeds? So another kind of hot tip here, you should make the seed not a hyperparameter, but you should basically like pick random seeds Sometimes I actually even use the random seed as a hyperparameter, right? Because in these type of hyperparameter frameworks, sometimes it'll choose a specific combination, let's just say 0.1 and 2 or something like that, and it'll just happen to get a lucky seed, and that lucky seed will result in a very good score. But if you ran the same experiment with the same hyperparameters of 0.1 and 2, again, you might get a different seed, and it might get you a very low score. So like, if the objective you're trying to optimize, right, if the training pipeline is something like a reinforcement learning training pipeline, right, which is very sensitive to the randomization and the seed, the random seed, then run your pipeline a couple times, right? Like use a couple different random seeds for the same hyperparameter combination, just so that you know for sure that it's not the random seed that's leading to the bad result. It's the actual choice of hyperparameters that's leading to the bad result. Yeah, different random initializations, the shuffling of the training data, the dropouts, patterns of data augmentation, like all of these things depend on the random seed, right? The seed is basically a number that you give to your computer that determines what, every time that it generates a random number, it's based on that seed. So it's basically like a way of controlling the randomness of your computer, right? If you give your computer the same random seed, then all random operations that it performs will be consistent. The variation results, we might run the same experiment with a particular search space, but with two different seeds for quasi-random search. Yeah, I do this all the time. It is all well and good to make comparisons of validation errors using fastidious statistical tests. More Jelly is back. Welcome back. Swag. Indeed. We are most concerned about study variance when trying to make conclusions that go beyond the level of individual point. Consider running the best trial n times to characterize the run-to-run trial variance. Yeah, so use run each permutation of hyperparameters a bunch of times with a bunch of different seeds, just to make sure that the it's not the seed, right? And you might get a bunch of different results, and then if you get a bunch of different results, you can kind of look at those results and see what the variance is there, right? After exploration continues, Bayesian optimization tools are a compelling option once we're done exploring for good search spaces and decided what hyperparameters even should be tuned at all. At some point, our priorities will shift from learning more about the tuning to producing the single best configuration. There should be a refined search space that comfortably contains the local region around the best observed trial. And once you have this refined search space, then basically use Bayesian optimization. So I think largely what they're saying here is that when you're first approaching a problem, you shouldn't, examples, RayTune fact. I think RayTune has a nice algorithms. They have like a table of all their algorithms somewhere. I don't know where this table went. But when you're first testing out a problem, you shouldn't go for something like TPE. Like when you're first designing a hyperparameter space and kind of trying and testing out a new training pipeline, do random search, right? Because random search will be better at kind of randomly sampling your entire hyperparameter search space. But what they're saying here is that over time, you're going to get better and better at crafting this search space, and you're going to get more and more narrow, more and more refined. And then you're going to get to a point where you have a very small and mature search space. And then at that point, you can basically choose something like a TPE or any kind of like Bayesian optimization algorithm, and then run it for a long time with that, and then you'll find the specific point in hyperparameter search space that maximizes your score or accuracy or whatever your metric is. So this kind of like two-phased part of like when you're still trying to figure out the problem, use random search, and then once you kind of have figured out the problem, switch to one of these Bayesian optimization methods to really get to the actual optimal performance. Determine the number of steps for each training run. There are two types of workloads when training is compute bound. Training is limited by how long we are willing to wait and not by how much training data we have on some other factor. Speeding up training is equivalent to improving training, and the optimal training time is always as long as we can afford. Yeah, that's true. There isn't some optimal amount of compute. You can always use more compute. When training is not compute bound, we can afford to train as long as we would like to, and at some point training longer doesn't help much. Yeah, so overfitting is a thing, right? Especially with smaller models or more narrow problems. You can eventually get to a point where training more for that model doesn't necessarily give you any performance. So there is things such as early stopping. So a lot of these hyperparameter tuners have early stopping to prevent overfitting and wasting compute in that sense. How long to train when training is not compute bound? Never tune the max train steps number. If the best step is to consistently use, you might benefit from training longer. Okay. So this is more just like look at your training and test curves, and here, training test curve overfitting. Yeah, so you can look. So when you're looking at your TensorBoard or your weights and biases plots or any kind of like logging that you're using, right? The training loss will always go down, right? So your training is this blue line, right? You'll always see it go down, but hopefully you're also doing testing at the same time, and you'll notice that at some point your training just keeps going down, but your testing starts going up, right? So up until here, up until this point here, as you trained more and more on the data, you got better and better on the test data. But then there's a point where you're starting to overfit, and what's happening is that you're starting to like memorize the training data, right? The model is just starting to basically be, rather than be good at the actual problem, it's just getting very, very good at memorizing the examples in the training data set. And what ends up happening is that it actually performs worse on the test data set. And that's called overfitting. So you want to be aware of that and look at your training curves, specifically the relationship between the training loss and the test loss or the validation loss. And if you see this kind of behavior where your test or validation loss starts going up and your training loss keeps going down, then you know that this is where the overfitting occurs, and then you can reduce the total amount of epochs that you train for or the total amount of training steps that you train for. So something to look out for there in terms of not wasting compute is make sure that you're not using a bunch of compute just to overfit your models. When training with the log loss absent regularization terms, we might see the training loss keep slowly improving until we reach floating point limits. Okay, so basically decrease max training steps if the training process improves. Deciding how long to train when a training is compute bound. In some cases, training loss keeps improving indefinitely, and our patience and computational resources become the limiting factors, right? Patience here is the key too. Like, as I was saying, most of the times in practice, I find these loops happen like in a weekly cadence, just because you want to train your models for long enough that you're actually getting a good result of what the performance is. But right, imagine if you could keep training your models and like you could actually train your models for months. Right, then at some point you would say, hey, okay, well, even though we can train our models for months, we want to like kind of iterate quicker, so we're going to limit it to like kind of a weekly cadence. So, or another limitation might come from the fact that you don't want to be training for months because that's incredibly expensive. So you get to a certain point where patience and computational resources become the limiting factors in terms of how long you're training your models. Tuning in multiple rounds with increasing per trial training steps. Yeah, so sometimes if your hyperparameter space is very large and you want to run a lot of samples, right, you can train for less long. Just don't train them as long, and then see if you can learn about your hyperparameter space with smaller models that didn't actually learn as much. Additional guidance for the training pipeline. Optimizing the input pipeline. The causes and interventions of input-bound pipelines are highly task-dependent. Use a profiler and look for common issues. So input-bound pipelines are training pipelines where the majority of your time is spent either gathering the data or processing the data or preparing the data to be fed into the model as a training batch. And sometimes this can be the result of having like NumPy or Pandas or some kind of like code like that. Generally, if you're using something like JAX or even PyTorch and TensorFlow at this point have basically they build a computational graph, and then they're very good at running that computational graph efficiently. But if you have kind of Python in the loop and you're doing this kind of just-in-time stuff, you can actually be wasting a ton of time of your training pipeline just shuffling NumPy stuff around. So use a profiler. So code profiling is a way of kind of understanding which parts of your code are taking longer and which aren't, and make sure that you're not spending a bunch of time outside of the training loop doing other things. So some common causes. Data are not co-located, causing I/O latency. So your data might be in some S3 bucket that's far away, and then every time you load a batch of data, it has to be sent over the internet, and that causes latency. So this is a common issue. Online data processing. So if you have a bunch of augmentation or a bunch of maybe you're taking some of your data, feeding it through one model to create a different type of data, and then feeding that through a different model. So like these kind of complicated multi-model pipelines. Sometimes you'll have a bunch of time just sitting here waiting for the data to pre-process, and your GPU utilization is pretty low. Instrument input pipelines, prefetch examples, remove unused features and metadata, right? Make your data as small and lean as you can. And yeah, use the abstractions provided by the deep learning frameworks, right? So the TF data set, PyTorch has a kind of a data loader and data set abstraction as well. And those are generally relatively optimized, right? They have people there's people that work every day to make the PyTorch data loaders faster, and the same thing with TensorFlow. So try to put stuff in the dataset formats of the frameworks as fast as you can, because those are going to be much more fast than any kind of manual data preparation and loading that you write by hand. Run evaluation at larger batch sizes than training. Run evaluations at regular step intervals, not regular time intervals. Saving checkpoints and retrospectively selecting the best checkpoint. Yeah, most deep learning frameworks support model checkpointing. That is, the current state of the model is periodically preserved on the disk. this allows the training job to be resilient to compute instance interruption. So another reason to do model checkpointing is this overfitting, right? So let's say you didn't create a model checkpoint until the very end of your training run, then you would end up with a checkpoint here that's actually worse than the model was here. So intermediate checkpoints are usually a good idea. Sometimes it's not necessarily a great idea because you're just kind of polluting your logs with a bunch of these checkpoints, and every time you create these checkpoints, it's like some amount of time is spent to create that checkpoint and save it to disk. So look at your training curves and try to figure out if you should be creating model checkpoints at the very end or intermediately. So keep track of the end best checkpoints. The best checkpoint is often not the last checkpoint, right? Particularly when the validation set performance does not continue to increase, but rather fluctuates. Early stopping. Setting up experiment tracking. When tracking different experiments, make sure to note a number of essentials like the best performance of a checkpoint in the study and a short description of the study. Found that keeping track of experiment results in a spreadsheet has a helpful result to this sort of modeling. So experiment tracking is important. There's a bunch of different products that help you with that. Obviously, everybody knows TensorBoard, but then there's also other products like Weights and Biases that help you with experiment tracking. So they basically keep track of all your losses and validation scores and all the different hyperparameters that you used for things. So yeah, don't try to make these things yourselves. Just there's a lot of good tools for experiment tracking and logs. I think TensorBoard is the default, but if you want to get more fancy, you can use something like Weights and Biases. Batch normalization implementation details. Batch norm can be often replaced with layer norm, but in the cases where it cannot, there are tricky details. Yeah, so these are different forms of regularization. They're basically making the data nicer, right? As the data flows through your computation graph, you ideally want it to be well-shaped. And what that means is you want it to be centered on 0, and you want it to have a relatively unit variance. So normalization is the process of taking data which isn't centered on 0 and has some weird variance, and basically normalizing it, which means making it centered on 0 and have a more reasonable variance. And you can perform normalization at different points in your computational graph. You can do it in between each layer, which is what layer norm is. You can do it for every element in the batch, so normalization across the batch, which is what batch norm is. And there's a bunch of these different types of normalization at different points in your kind of pipeline. Some of them are more complicated than others. Some of them are more sensitive to hyperparameters. So I think here they're kind of just advocating for layer norm, just so you don't have to deal with batch norm. Yeah, and then here's an additional complexity. If you're using multi-device or like parallel training pipelines, the batch norm statistics are going to be different on each device, so this is an additional complexity. Anecdotal reports calculating these normalizing statistics actually works better in practice. Decoupling the total batch size and the number of examples used to calculate batch norms is particularly useful for batch size comparisons. Yeah, and sometimes when you're using some training code, you'll see what's called like a warm-up period. So if you've ever seen that where it's called like a warm-up, right? What it's actually doing is it's actually building up these hyperparameters and momentum. So like optimizers and regularizers, such as these different types of normalizations, a lot of them have these like momentum terms that like build over time. So what you're doing in warm-up periods, when you're doing warm-up as part of your training, is you're basically allowing those momentums and those exponential moving averages to basically get to a good point before you start pushing gradients into your network. Multi-host pipelines. Make sure your pipeline is only logging and checkpointing on one host. Batch norms statistics are synchronized across host. Critical to have seeds that are the same across host. And sharing data, sharding is usually recommended. So sharding is a form of taking a data set and kind of breaking it into shards, right? A shard is like a little piece of something. So a sharded data set is just a data set that's been broken into little pieces. So sharding usually refers to like kind of clever ways of taking a data set, breaking it into different chunks, and then feeding each of those chunks into like different machines. TensorFlow has a way to basically take a data set object and then shard it. I think PyTorch does too. A couple different questions here, and then acknowledgements. I think we're already, yeah, we're basically at the 2-hour mark, so we're probably going to end it here, but we did end up skipping through a lot of this, so there's a lot of stuff that we glossed over. Hopefully I managed to pass a little bit of experience and knowledge and expertise that I've gotten over time when it comes to hyperparameter tuning. In terms of hyperparameter tuning libraries, there's a lot of them. Hyperopt, Keras, Weights and Biases Sweep, and RayTune, I would say, are probably the ones that I would recommend the most. Hyperopt is probably the easiest one to use because it doesn't have any additional stuff. These other ones are kind of like combo products. So Hyperopt is very standalone, and you can use it just by itself with whatever other stuff you want. Keras Tuner obviously requires you to be using Keras and TensorFlow. Weights and Biases kind of comes with all the additional baggage of experiment tracking, so you need to, it's kind of like a full buy-in. If you're using Weights and Biases for experiment tracking, then using their Hyperparameter Tuner is also quite convenient. But if you don't want to fully buy into the whole experiment tracking with Weights and Biases, then you might be better off using Hyperopt or Keras. And then the Ray Tuner is actually very similar to Weights and Biases in that Ray is kind of an orchestration framework. It has a bunch of extra stuff in addition to hyperparameter tuning, and it also requires buy-in. So things like Weights and Biases and Ray, they're more multi-featured machine learning products that are selling to you a variety of different machine learning features, and they force you, right? They're kind of opinionated. If you're going to be using the Ray hyperparameter tuner, you're also going to be using the Ray kind of scaling and all these other crap things that they have, and data processing and all that. So if you're building a big production machine learning pipeline, something like Weights and Biases and Ray is probably the way to go. If you're doing experiments locally on your computer just for fun, or maybe you're part of a small startup, I would either recommend Keras if you're using TensorFlow and Keras, or Hyperopt if you are using something like PyTorch. But yeah, that's it, guys. I think you have everything you need to learn how to do hyperparameter tuning. Hope that was helpful. Hope you guys found some of that, and drop in the Discord. There's a link in the description if you want any questions. I check the Discord and I answer questions. There's people on there asking stuff, and yeah, you get a free machine learning engineer to answer your questions. So thanks for watching, like and subscribe, and see you guys tomorrow.